I will try to cover a few things today. I will begin like travel is business. I have to cover a lot and include what is going on, what is going on, both sessions.
Very good video.
Very good. You have lunch and tea and everything. Today, what I'm going to cover to start with is we talked about US EPSU model. Just to give you a very brief idea about it, it is a very good model. And most of the water sensor design approaches we talked about, it can be basically tested or implemented for modeling purposes. And the manual which is available in this EPSM is informative. What I will suggest to you, take a very simple example first. Whenever you're looking for a new learning tool, the example should be as simple as possible, and for which you can have physical feeling. You can understand that okay, the results which I'm getting will certainly be close to what I'm seeing. The moment you make it more complex, you start with the complex. It will be very difficult to figure out whether the results which are getting. But you can do some basic calculations outside the tool using your calculators or maybe activity. And you can check results. So that is one of the essential aspects. Like for example, maybe using a cycle, and you start looking at different sizes of pump size, river tank sizes. You can do some calculations by yourself. Okay, what is the size of how much water I can get based on those codes and everything. That can give you the basic information, and then you will have more confidence about using those codes. This is how we can learn. This has been my approach too. That's why I'm suggesting rather than going for a big problem altogether, and then you will not be able to make out. And there is confidence about using software because you have black boxes. The data which you're putting in, similarly, they will be out. And what is happening in that tool, this is very important to understand because ultimately, you have to justify your results. There should be some sort of a reasoning why you're getting those results. And until you are able to follow that aspect, you will not be just able to justify your results. That is one of the most important things using those platforms. You should very well understand why you're getting the results. It should be only possible if you have a good understanding of those, how you're getting good results. Just a suggestion. Have you understood? Okay. So today I'm going to talk one example about where we used very briefly the software. So different approaches, as I said, most of the approaches which we discussed about can be implemented. And over here, they don't call it rainwater tank, they call it rain barrels, which is the same. And also, in reality, what we're doing is the rainwater tank is that we are not only storing water in the tank, and so there can be two things which we can do. One is in the software, we have rainwater tank, and then rather than this will be the last possibility of rainwater tank. So what happens with the rainwater tank is that it has from the flood mitigation or reducing the flow in the stormwater, so the network is concerned. The water is coming in, and then it has the orifice, which is discharging at a reduced rate to the stormwater network. Okay? That means we can reduce the peak flows to that approach. That's one thing which this EPA model is very good in. And you can change the size of those orifices, which will change the flow outside the rainwater tank, which will be entering into the storm. The another thing which is the reality is that we have a tank, but we are also using water for alternate purposes, as an alternate source. So we can mimic those type of situations in these orders. That our discharge, which is coming out, is not only during the rainy season to that orifice, but we are taking out water in the road. So that how we can mimic that type of situation is something give it that. So every day we are taking certain amount of water based on the demand. But this using as the orifice, providing orifice is very simple approach. But we are also using water from the rainwater tank. So you can also have one output from those tank on a that I'm using 400 liters or so many liters water on an everyday basis. Really water is available. So you can use these type of things too. So these are some of the approaches we talked about. Yesterday, I showed you one table where which of those water substitution design is suitable for providing, whether it is suitable either for peak flow reduction or it is suitable for water quality management, or it is more suitable for from the aesthetic point of view. But this table is another table, and which is more talking about where these type of approaches are suitable, whether it is household level, medium density level, high rise, and so at suburban level, subdivision level, and urban retrofit. So this is another reference material or table which can also be referred along with the table which we talked about yesterday. And there is a reference already provided from where I picked up this table. And this reference is available publicly, which you can also call. So,
Question marks are there?
so question mark may be that information is not very well available. So, like for example, the bioretention swells. The question mark is because not necessary that it will be at a house scale level until the area of the house is quite large. Okay? So there will be one or two question marks, and you can see that means that information is not. The author was not very sure about whether they are 100% suited for those types of provisions or implementation. Thank you for writing the paper. Sorry?
नीचे लिखा होता है.
Yes, yes. I think in that, in detail,
Possibly suitable.
it is written over there too. Yes. Okay. So this is a publication which you can see from the Goida Institute of Water Research. There is a report, complete report available, and that's what you can see, complete reference over here, and you can download that document, whole report from that reference. It is available there, and then we have described the complete methodology, how to use EPSM model in that report. So basically, the first is to select a suitable site where we are going to implement it. Select a modeling tool. Which modeling tool will be suitable, because there are a number of modeling tools available. I think I will show you in one of the slides here. So these are the potential models which are available in the market. Some of them they are free, some of them they are charging significant amount of money. So each of the model they have some specific applications for specific purposes. But you can see the further information about these models in the same report I'm talking about. So out of those, we talked about PCSIM, that is similar to XVSIM. It is more, I think, the Australian focused, and there are a number of other models. I will talk a little bit more on music model, which is coming from EPA, which is more stormwater focused to understand the quality aspect of stormwater. And then these are the other models which have a combination of hydraulics and hydrology models. So to get more information about these models, I think you copy or download this document which is available and see, and this can be a reference material for you. So select a suitable modeling tool depending upon what you want to do. Okay. Some models are more focused on urban areas, some are more focused on rural aspect, more have a combination of hydraulics and hydrology both, and some are only specific, either talking about hydraulics or hydrology. So select a suitable model, construct continuous runoff modeling. So nowadays, I think those who are working in the hydrology area, so either it can be a bank specific modeling for hydrology looking at a particular event based, or it can be a continuous simulation. So nowadays they are more talking about continuous simulation because that gives a better out. You know the situation before that event in a continuous simulation. Otherwise, so it is simply to analyze event modeling. Continuous modeling needs much more efforts, but it gives a better outcome. Then calibration and validation, which is one of the most important aspects of, and there was some discussion going on that we don't have how we use it. Until we have calibration, validation processes. The normally what we do, if we have one year data for a year, 6 months you can use it for 6 months you can use it for validation. Depending on how much. But to get flow data is the most difficult part. Or other question, if you are looking for a larger area for your modeling and you have some data available for a smaller catchment of the same big catchment, then you can calibrate and validate your model for a smaller catchment, and you can use all those variables, parameters. Although the situation or the outcome can be slightly different, but at least you have some basis to justify your work.
Nowadays, there is another methodology coming out, PUB basins, prediction in ungauged basins, and then we have the control stations or the nearby stations used for calibration and validation.
Yeah.
So the coming.
But still you need some data from those stations.
Right.
Yeah. So calibration validation is one of the most important aspects. And select scenarios means what options you are going to model. And that is based on a particular project, based on the conditions which you have to look into. There can be the climatic conditions, they can maybe putting different type of infrastructure to see what impact it is going to have in the overall hydrology and hydraulics of that infrastructure or the catchment. So select data for long-term continuous simulation. So normally we're talking about climate data over here. And then we conduct simulation, see the peak flows, runoff volumes, and analyze those scenarios using that any model. Over here, I'm talking about more about EPA SUB model. So the model selection criteria, this is something based on the work which you want. This to select a suitable model, I think you have to understand what is your aim of your study. Okay? That will help you because each and every model they have some positives and some negatives. So you have to think about your objectives and then you select a suitable model. So these are some of the aspects, not limited to, but you can understand, you can have some sort of a rough idea that what criteria, what thinking you should have in selecting a suitable model for your purpose. The simulate runoff flow in the urban environment. This was something we are looking for. We are looking more the stormwater runoff quantity through that area which we decided to model. Effectively simulate both overland runoff development in the urban environment and close to the stormwater drainage system. So, because the system was laid over many years ago, and then there was further development in the same area by subdivision. So, what we were looking at, how much will be the overland flow and how much will be the flow through the stormwater drainage network. Transport overland overflow to catchment outlets, and in the case of an outlet at overflow capacity, routes flow in excess of the capacity. Basically, what we were interested to know that we were aware that the infrastructure capacity is low, but with the change in the urban area, what is happening in terms of the overland flows. So these were some of the our requirement for selecting a suitable model. So, and then it continues. Basically, we are also looking the water quality simulations in that area. So, looking all those models, then finally we selected US EPA, which allows the user to quickly and effectively access model calibration, process long-term flow time series, and rapidly import data collected in geographical information systems environment. So you can have your GIS applications too with this model. So this was our catchment area, and we were looking at the capacity of the Trent stormwater system in a 45 hectare area, where 577 allotments during 90 to 95, 200 additional homes added just before the study which we conducted. There was significant change.
So how this subcatchment are delineated? It is so much symmetrical, which people want.
So this is symmetrical. What you mean by that? Sorry.
Means, what is the procedure for designating the subcatchment?
So we used because we put another layer of stormwater network system, the topography, and the sizing which we got from the local municipality or the water authority. So we put all the data into the EPA net model rather than manually entering into it. We brought those data files, and it has the capacity where you can use those data directly. So these were some of the scenarios which we are looking for. Initial impervious area, which was in 1993. Then we looked at there is an additional 20% impervious area which has increased because of the future development before this study. We used this 1993 because there was stormwater flow data in that at the outlet level. So we used that for calibration and validation. And then we start putting rainwater tanks of different sizes to understand what impact it is going to have on the stormwater flow in the pipes. So what we found was that for 1 year ARI to, I think, a 10-year ARI, what we looked was that in the initially, based on the 1993 flow development level, the 1 year ARI was 0.9 meter cube per second, and which increased over time. But even by putting rainwater tanks in the houses, in almost each and every house, we couldn't see any impact of change in the flow. And the reason which we picked up later was that the capacity of this network was very limited, which we couldn't realize any changes, reduction in the flow, even putting rainwater into a bigger size. So these are the type of studies which you can take by putting different scenarios. This is a very particular condition which may not be everywhere. Rainwater tanks will have certain impact, but the very old development, the reduced capacity of the infrastructure, even by putting rainwater tanks, to make much of a difference. But they conducted this work further by putting retention ponds in some of the areas, which certainly made some changes in stormwater. I don't have that part with me at this moment, nor it is included in the report, because they conducted that study once the report was developed.
What is ARI?
Average recurrence interval. The one in
Return period.
return.
So that capacity was showing that how much volume is retained. Last column, volume retained in million liter per annum.
So basically, in this case, we are using rainwater tanks for internal applications. Okay? That is the retention in those two scenarios. So application for internal water use, that's what the retention
The second part.
through the rainwater tanks. So the rainwater tanks one, just the orifice, and then they are outlet using water for houses from the rainwater. So if you see this scenario over here, scenario which is scenario retention is in scenario G. Okay. So in this case, we use rainwater tank for internal applications too. So the conclusion is the contribution factor to the smaller reduction in the peak flow or the limited capacity of the pipe drainage system, which was approximately equal to 2 year area, due to relatively flat grade across the catchments. So that was the limitation. So it is just to show you that how you can use all those water system design approaches using EPNet model. So we also use a similar model for another case study, and the idea was for using that we were looking. This was a part, and then this was a car. This was a car part where there was a lot of runoff coming to the garden area. So the managers for this part, they were looking if you can capture the stormwater runoff from the car part, and if you can store it and then we can use it for irrigation purpose in these areas. So we used EPSU model just to see how much the runoff we are getting. We just use for hydrological purposes. The idea was that taking a 9-year the climate data, we wanted to see the peak flow over that time. And the understanding was that if we design our pipe network or the collection system for that peak, whether we should take the peak value or we should find out a suitable value where our cost of the infrastructure would be less. And we are losing on the limited amount. So what we did, we used this EPSU model and we plot a graph, runoff in meter cube per second, and number of events, rainfall events. And that was for 9 years data, daily data. We got a plot like this for around 900 events, 9,000 events. Then what we did, we looked that initially the maximum flow, peak flow is roughly around 6.6 or 6.8. Then how many events are there where we are getting a high peak flow? So what we did, we plotted initially roughly around the high 91 events. And then we got this type of curve and we realized, okay, roughly around 1.5, 1.6, we are losing only limited events by taking the peak flow of 0.68 for designing our infrastructure. Rather than we miss out these few peaks and design for remaining what the runoff which is coming. So what we found was that by taking this 0.8, the size came roughly around the commercial pipe size, which we got 0.67 millimeter. For the peak flow, for taking water from the catchment to the rainwater storage tank, it was such a diameter of 0.67. But when we start reducing this, considering those peaks to the lower peaks, then what we found that if we take the around 0.25 over here, something over here, then the size came roughly around 450 millimeter. We further reduced to 0.15 to check. That size came to 0.375 millimeters. So then we looked at how much water we are actually losing out, because by not taking those peak flows. Okay? Then what we found, the loss of the stormwater due to reduced capacity in meter cube. Okay? So, and that percentage loss of the overall collection which we're getting. So by reducing from 0.68 to 0.41 peak, we reduce 0.26% of total water annually which we're getting. So that was the very tiny amount of water which we lost. And then we were going up even up to 0.2, we were getting reduction of 0.18, 0.81 of the total runoff annually interest. So what I want to say over here is, it is not necessarily that you pick up the peak flows. You look into the economic cost of it and see how much water we are losing by not taking the peak values and what will be the most suitable value for the area. So you can conduct that sort of very simple analysis, and then you can see the reduction in the cost. So even by taking if peak flow of 0.25, you are losing only 0.8%, which is a tiny component, but you are saving around 32% of the overall cost. But this is just one example to give you some idea. Not necessarily this situation will be applicable everywhere, but these type of analysis can help you in selecting a suitable infrastructure.
We took the climate data of 9 years.
Yeah.
And we are looking for a particular year. So in 1 year, we are able to use only 2,664 meter cube of water.
So in this, yes,
This is for 1 year data,
well,
in 1 year.
yeah, but we analyzed for 9 years. Yeah. In 9 years, we found that only there are 8 or 10 peak events of peak flows. Rest of the year, rest of the 9 years, there is flow is less than those. So those, if you see a little bit more these, we put them in a descending order. Okay? So maybe this 0.68 maybe in 2000, say for example, 18 or 19. The other maybe in 2000 in any other year. Okay? But we put all that up in descending order. And then we selected that okay, let's not consider these 5-6 peak flows and then see what will change in the cost and how much water we are losing out of it. Does it make any sense?
Yes, sir.
So maybe these are the type of analysis one can do it. And there is a complete publication on this study, which I'm happy to share. We published, I think, 2-3 years ago. There was a undergraduate student working with me on this design aspect of irrigation system, and we used sprinkler systems because they are quite efficient in terms of saving. So those who are interested, I will share that with you so that we can get this copy of it. So the purpose of this showing that not necessarily that you look every time the peak flows, but also consider the economic aspect. So to continue, so far what we have done in terms of water conservation design in either the greenfield areas. This is one example, Canberra. Canberra, in that is the capital of the state. So what the department over there was interested in to find out that how we can reduce the flow reduction in household water demand by 25%. What can be the means in it is an already developed suburb or the town. So these were some of the objectives which or criteria objectives they asked us to investigate. 25% reduction in household water demand, 20% reduction in wastewater, peak stormwater flow no more than redevelopment levels.
India was given by 30.
But yes. So they asked us, okay, this is the suburb, 13th suburb in a particular catchment, the total area and the population and number of houses. That includes roads, open space, and other. So they wanted us to do some analysis and see what can be the means to achieve those objectives. So again, there is a publication which I will share with you to give some idea that it is not only in the news developments, we can also think of some options in the existing developed areas too, based on the form of the development. So what we looked for, the allotment is still, there were rainwater tank options and greywater system. These two options, and the development scale from the stormwater point of view, we looked cross pollinated traps, ponds, bioirrigation systems, and swales. Okay. So for looking the water balance aspect of reducing the potable water supply, which was target of 25%, we used EcoCycle, as I talked about, EcoCycle, and did the modeling. So that publication will give you some idea that how we did and applied that EcoCycle model. But I talked about another model which is available on through the same website, an e-water website. And this music model, this is coming from model for urban and stormwater improvement conceptualization. So the music is the short form of that model. Okay. So in that model, what you can do is you can model each and every suburb. You can see the runoff. This is how very simply you can draw. You can put the area, you can put the infrastructure which you want to put. So this is how we did it. So all for these suburbs, what we looked for bioretention system, then we looked gross pollutant traps, then we also looked for ponds, and then we connected another few other suburbs based on their sizes. And then we also provided bioretention system, cross pollutant ponds, and then ultimately we try to look at the outlet, how much reduction we are getting to those systems, and we by trial and error we change the sizes, change the type of infrastructure which we want to put more sustainable design, and then we look the impact of those by trial and error methods. That ultimately, what will the improvement in the water quality and what will the reduction in the flows. So this was another technique which we used along with EcoCycle. So these are some of the options which we considered. One was the base case, which was that okay, under the existing conditions, they're getting water from the pipe supply for all the purposes, and they're getting wastewater discharge and the stormwater discharge into the network. That was our base case. Then what we did is centralized system plus rainwater tank for few purposes. The purpose there, toilet flushing and garden water. Okay. So then we looked again how much water can be saved. In the third scenario, instead of using rainwater tank, you want to use the grey water. Okay. And the fourth one was the combination of rainwater and grey water both. Okay. So these were the combinations.
Water will be used if anyone.
Sorry.
This water will be used anyone taking purpose.
What we did, we collected grey water from the showers, and the black water was going again into this wastewater network. So there is one disadvantage of these approaches which we have to keep in mind, that the moment we reduce the flow in the sewers, what will happen?
Rating.
There will be chances of blockage. So we have to keep in mind that aspect we will design these systems. Because we need minimum flow velocity to take the solid particles away. And this is more critical in the transfers. In the transfer, flow is very fast. So sometimes we have to flush transfer. Or otherwise, we have to provide, even in the normal circumstances. Otherwise, we have to provide, because the flow is less, we have to provide a high gradient flow to create the velocity right for transportation of soil. And if you provide it more so initially in the transceiver, then it will have an effect on the further in the network. You have to take the inward level of that pipe and you go further deeper and deeper. So again, there is economics that plays into whether it is okay to flush only few pipes which are critical, or you design your whole network significantly deep, which will have greater impact on the overall cost of the system. So when I was doing my master's with Professor Swami over here in guys and civil engineering department, he published a paper on that aspect in American Society of Civil Engineering. That was picked up by using EPA model guys to see. We suggested some aspect of what is the flushing of products, what is the minimum velocity which is already but basically in the transceiver. So these were the four scenarios which we considered, which are very simple. And based on that, what we found was, and we also looked two types of demand management. One is the high demand management and low demand management. And what we found was that in case of, if you are putting rainwater tanks in 100% of the houses, we are able to achieve only 22% reduction in the potable soil. Like all that information is coming using EcoCycle, which we talked about. But if we have a high demand management, that means we are reducing the water demand, water supply. Okay. So, or we can say the water reducing the water demand, the water supply, they are linked together. So the high demand management, if you have high demand management, then maybe that we can achieve up to 33% reduction in the potable supply. Okay. And similarly, if we have only the grey water system, it will be 13% in low demand management and 22% the high demand management. And if we have combination of both rainwater tank and grey water systems, then we can have, if we are implementing this type of system in all the 100% houses, 14,000 homes, then we can achieve up to 34% reduction in the potable supply, or if high demand management 40%. So this is, so by mathematically simple mathematics you can get in this case that if you are providing more rainwater and grey water to achieve 25%, how many homes you need the both systems. The simple mathematics. Similarly with high water demand, if you are achieving with the 100%, 41% to achieve 25% in how many homes in total we need these type of systems. So we provided that information to the authorities there, and based on that, what they did is they amended their planning control policies. It is not very easy to implement such a high number system with such a high number to achieve that outcome. But they got some information based on that. They changed their policies. And what they did was the planning control to facilitate installation of rainwater links to greywater systems. Commenced a government-funded rebate scheme for rainwater tank the result of the system. It is not possible to achieve all those outcomes in a single day, but they change their policies and they start providing subsidies to encourage the residents for looking for the installation of rainwater system. So these type of studies can also help in providing information to the policymakers. So this is just one example you can use different tools, different studies for informing policymakers, the government, the regulators. So I will share a complete publication on this study too, which can be a reference material for you in future when you go to a different part of the organizations or different organizations. So this is one presentation covering, this is the end of the rainwater tank chapter. I will go through another chapter now for presentation. We want to cover this on Thursday. We changed the schedule, so I'm presenting it now. It is talking about a little bit more on policies, regulations, capacity building, and community perception. And this is not only for water conservation design. These aspects are equally important for adaptation of any other infrastructure or policies. What is the importance of having policy and regulations enhance capacity building is the capacity of the those who are working in this area, their knowledge, their experience, their skills. And community perception is whenever you implement any new aspect, what will be the response of the community? This may be a little bit more theoretical and moving away from general engineering design aspects, but it is very important on the overall adaptation process. So it covers about the policies and regulations which are, and it is more on, so it will be more Australian focused, but similar aspect will also be important in any part of the world. Then we talk about the capacity building and community perceptions. So this is a diagram which I have adopted from the publication just for this presentation. This talks about different stages of adaptation. So first stage is related to the technological aspect, which is a review of the water system technical characteristics. Then we look for where these type of systems already been implemented. And then look for the designer aspects, how the current guidelines, approaches for design are relevant. And then see what parameters are important for different approach. In stage 2, what are the current urban planning and regulation processes? Because as we talked about initially, as we discussed initially that water system design, it is incorporation into the urban planning aspect. So that's why the second part, this stage second is related to that, about the urban planning regulation and processes, how the water system design can be incorporated into the overall urban planning. Understanding about the local plans, policies, infrastructure programs. And then environmental aspect and constraints, requirement for urban developing plans. Then based on urban planning, all that information will go into urban planning parameters. Okay, thank you.
Shall we take a break?
You can take a break for 5 minutes.
We can take tea for